Okay, so yesterday we talked about logarithms for what's probably the first time I'm imagining most of you ever saw logarithms. Why are logarithms even useful? Like, what does a logarithm do to a number? Makes it considerably smaller, yeah. I mean, we did an exercise yesterday where I said, find the log of some of these numbers. And we don't even need our calculators for these. If I ask you for the log of 10, the answer was 1. The log of 100 was 2. And if you kind of move that forward quite a ways, the log of that number is 5. And after a while, I started to figure out the pattern. The pattern was, well, it tells you how many zeros the number has. Right? Essentially, a logarithm in its base 10 format was a way of trying to figure out just how many digits a number has. So technically, I guess 10 is a 2-digit number. What it actually tells you is how many zeros it has afterwards. Does that make sense? And you can kind of do a number in between. If I ask you for the log of that number, you can probably guess about what it's going to be. Because, I mean, it's not quite this digit here. It's not quite up to the next, 10. This run right here would have 1, 2, 3, 4, 5, 6. So imagine this is like 5.8 or something along those lines. So, does that make sense so far? That's what logarithms do. It's like a square root. It's like squaring. It's like multiplying, addition, subtracting. It's basically it's an operation on numbers. One of the second things that I wanted to impart on you is the fact that logarithms are actually useful in life. You probably will never care, to be honest. I never really cared. But I did show you one example when I did all of a sudden have my own aha moment. Things that grow often grow logarithmically. That works. Like, for example, you guys. You're probably at the point where you're not growing much taller anymore, right? And so if we were to sketch a graph of this, the graphs that we learned about look something like this. They usually start right here, and then they get taller and taller and taller. But, like, although this graph is rising little by little, it's more or less kind of flatlined. Does that make sense? So, like, you would grow according to something like this. When you were in your first couple of years of life, yeah, you grew quite fast. So I think I found you some graphs of like newborns and their head size, or newborns and how long they are. Because like when Kinsey Ann was being measured as a doctor, it's kind of a logarithmic graph. Plants actually do the same sort of thing. Sometimes we don't actually use a logarithm. We use a natural logarithm, which is ln. It's pronounced lawn, as in like your front lawn. And basically, it's a logarithm that grows according to like what's called a natural sort of curve. What else were the highlights from yesterday? I think probably the biggest thing I need you to take away from yesterday's notes is that the domain of this graph is not x's element of the reals, like it's always been. What's the domain of this graph? Yeah, x is to be greater than 0. If you were to have, like, say, a graph here, and this is how, like, tall someone is on this side, and this is how old they happen to be, it might even make sense that you can't have numbers over here. Because you can't have a person who's negative years old. Does that make sense? You might also argue that you really shouldn't have this part of the graph here because you can't have negative height, perhaps. But hopefully you'd buy the argument that you can't have a negative age. Right? So the whole half of the graph over here is gone, which led to a diagram that looks something like this, showing that these logarithmic graphs, like this one right here, they actually have a very similar sort of shape to them as the exponential graph we have. This one right here is considered exponential, where it starts slow and then shoots up really fast. Well, this is a log graph, and it shoots up really fast, and then it starts to slow down slowly but surely. Does that make sense? They're actually, the word we use for them is they're inverses of each other. You guys don't probably need to know that word for the diploma or anything that I test you on, but that's the word we use where they're very similar. You can almost like draw a line right through the middle of this thing, a diagonal line. And if you like turn your head kind of sideways, they're actually mirror images of each other. Can you guys visualize that? Yeah. Okay, today what I want to do is talk a bit about some of the rules associated with logarithms. This is actually a complete rehash of what my Dash 1 kids do, which is one of the more challenging sections. So I need to apologize in advance. I have no control over what they put on the diploma, but this is probably one of the more challenging sections we have. There are 4 rules probably 5 rules actually. 4 on your data sheet and a 5th one that's not on your data sheet that I need to show you how to use. And then I'll show you a few questions towards the end of the notes that are like old diploma questions. So the first one I want to start with is one that was actually in our notes the other day, and I kind of skipped it. It talks about how exponents and logs are very similar to each other. Let me show you an example of an exponential equation. It could be like something like 3 to the power of x equals y. This one's kind of silly because I guess the y's and the x's are backwards, but essentially you have something that's like an exponent as a power. How many 3's are you supposed to write? You just keep going, right? That's the whole point of an exponential function. If I give you x to the 3, it means write 3 x's, right? If I give you 3 to the x, it means 3 over and over and over. Tell you, well, whenever you're allowed to stop. Okay. When we talked about exponents, they have what's called a base right here. This lower number is the base, and the top number is the exponent. There's actually a similar thing to logarithms that I was showing a few of you at the end of last day's class, where sometimes what we'll do is we'll throw a little number down here. Okay. Now, if we don't write a number, it's actually assumed that this number down here is 10. Yeah. And the reason why it's 10 is that whenever we do a logarithm kind of thing here, basically what we're asking ourselves is, how many 10s are there in the number 10? And you'd say in the number 10, there's 1 10. How many 10s are in the number 100? And you'd say there's 2, because it's 10 times 10. How many 10s are in this number? 5, because it's 10 times 10 times 10 times 10 times 10. Well, 10 is a really nice round number to work with, but we don't actually have to do it with groups of 10. Let me show you a different example here. Need more room. If I were to ask you for the log base 3 of 27, here's what this question is asking you. How many groups of 3 are there in the number 27? And so you might do something like this. Like when you learned how to do this way back in the day, you'd say 27 is 9 times 3. And that's like a couple of 3's. So you'd say, I can write 27 as 3 times 3 times 3. So you're a little ahead of me. How many 3's did we write? We wrote 3 of them. That was a bit confusing because the number was 3 and we used 3 of them. So maybe I should try another example. Let's try this one. Log base 2 of 16. What this is essentially asking you is take the number 16 and make it smaller. Tell me how many 2's are in the number 16.
How do you make the base 2?
I'll show you guys that in a second. If you don't mind. Sorry, some of your calculators have that ability, and maybe I've shown you, some of them don't. The answer is 4.
Yeah.
The reason why is that 16 breaks up into, like, say, 4 times 4. That's 2 and 2. That's 2 and 2. So the question is, how many 2's are there in 16? And the answer is, there are 4 of them. Does that make sense? Let me try a few more just because repetition sometimes helps. If it was log base 10 of 100, the answer is 2. Because this basically asks, how many 10's are in 100? And you'd say, well, 100 breaks up into 10 by 10. So there's 2 of them. Which yesterday I showed you is really easy because there's 2 zeros afterwards. Which is true. But today I have to start showing you some rules about logarithms where what if we're not doing it in groups of 10? Because 10 is pretty straightforward. Can I do one more? Just to make sure we got this. So if I asked you for log base 4 of... No, something different here. Yeah, let's do that. 64. What are you being asked? You're being asked how many 4's are in the number 64?
3.
Yeah, because 64 breaks down into, what is it, 8 times 8? And then that 8 is a 4 and a 2. That 8 is a 4 and a 2. So you might argue, okay, well, there's one 4, there's a second 4, but look, 2 by 2, there's your third 4. So the answer is 3. Okay, so first thing I need to do is then show people how to do that small little base, where when there happens to be this little, oh boy, it's a long ways down here. When there's this little number down here, you need to know how to put it in your calculator. Because some of you have a calculator that can do this and some don't. So, first of all, you probably need to have not an 83. I don't think any of the 83s do this. So you need to have an 84. Sorry. If you have an 83, I'll show you another way, by the way. So if you have an 83, here's what you do. You don't press the log button right here. You press second, and then the number 0 is the catalog. And what this does is it literally goes through every single thing your calculator can do. And what we want to do is find a log. So I press the bracket over here for L, and then I keep scrolling down until I find logs. Now, my calculator on the screen, and any of you have an 83, you don't probably have this, but some of you might have right underneath log, there might be log base. Any of you have that that are trying it? Log base. If you happen to have that one and you press that answer, it'll make your calculator do this, log with a small little box here and a bigger box here. Basically what you have to do is put the little base number in the small box and the number that you want to find the groupings of in the big box. And if you do that, it'll tell you your answer. For sure. Okay. Well, this isn't going to work for YouTube because I don't think your 83 has that availability. It only works if you have an 84. Okay. Now, there is another way around this, though. So what I'm going to do now is start showing you some of the laws of logarithms that there are. This slide right here shows a couple of rules involving exponents. And hopefully you remember these rules because we've used them already. If you multiply exponents, it's very similar to adding them. If you divide them, it's like subtracting. If you put them in brackets next to each other, it's like multiplying. You guys remember these rules? Well, logarithms have some rules of their own too. Here are a couple. Like if you have two things that are times by each other, it's the same as adding them. Here, if you have two things that are divided, it's the same as subtracting. This is a really long way of me getting to this point. Here are the 4 rules I need to show. Okay? So these are on your data sheet. Give me a few minutes here. Let me walk you through some examples. Okay? So, can I skip down to this one here first, though? So even though this one's not necessarily next in our notes, I want to skip to this one to now show you how to do small little bases in the bottom. Do you guys see how right here there's log small bc? Okay. If you had, like, say, log base 3 of 9, here's how you can calculate it. If you cannot type this in your calculator, because you have an older style calculator, it means this. It's the log of the big number right here, which is 9, divided by the log of the other number, which is 3. And then a in this case right here, we're just going to make that the normal logarithm without a base. So if you have your graphing calculator, let's try a few of these here. If you can't type in like the log with the little base thing, try this. Try the log of 9 divide by the log of 3. Essentially, I'm saying how many 3's are there in a 9? And the answer is 2, because 3 times 3, 2 3's, is a 9. Let me try a few other ones that I had done on previous slides here just to confirm your work. So where else was I working here? Let's try log base 327. To type this in your calculator, if you don't have this ability, go log of the big number, so log of 27, and then divide by the log of the little number, the 3. How many 3's are there in a 27? There are 3 3's in a 27. Because 3 times 3 times 3 is 27. Or here, log base 216. So here's how you type this in. Go log 16 divide by bracket log 2. This basically, what you're asking your calculator to do is tell me how many 2's are there in the number 16. And the answer is 4. Because 2 times 2 times 2 times 2, 2 to the power of 4 is 16. This is actually on the first page is one of the rules I want to show you at some point, but why don't I skip ahead to where we were here? Let's talk about some of these rules. So here are some numbers that you're applying logs to. You're doing log 12 and log 2. Do you guys have a formula sheet nearby, or at least have the sheet before us listed nearby? You see how here, this is actually going to be this rule about logarithms here. Here you have a log, and here you're adding another log. Well, there's a rule of logarithms that basically says what you could do is rather than have two individual numbers get added, you could times them instead. So look, here you have log 12, here you have log 2. What is this going to be equal to? Anyone want to take a stab at it?
1.3.
Well, don't tell me the decimal number. The log of what number? 24 is the answer. The reason why is that 12 times this by 2 to give 24. That makes sense? Now, if you want to confirm that, I mean, take your calculator, just double check. Right? Log of 12 plus the log of 2 is 1.38. The log of 24, ta-da, also 1.38. But once you get these sorts of patterns, it's not quite so bad. Like here, there's log base 2, 5, log base 2, 6. Well, this means it's log base 2 of 30. Where did the 30 come from? 5 and 6, yeah. Let's just confirm just to make sure. Can I type in this calculator a log base, like log base 2, 5? I can't, but I can do the way around it. So I can go like, say, log of the 5, divide by the log of the 2. Then I'll add the log of the 6, divide by the log of the 2. Gives me 4.9. And if these rules are correct, adding should be the same as timesing. So 5 and 6 is 30. Log of 30 divided by log 2 should be the same thing. What this basically asked is, how many 2's are there in a 30? Does 2 go into 30 an even number of times? No. No. What's the closest numbers that 2 goes into? It goes into 2, 4, 8, 16, 32. So there are 5 2's in a 32. So therefore, this answer is just slightly under 5, because if we're looking for how many 2's go into a 30, it's 4.9, because you can't quite fit all of those 2's in, because it's not the number 32, it's only 30. Does that make sense? Logarithms are very strange. It's a very roundabout way of trying to answer a question. Okay, let's try this next one here. What if we were asking you to try to subtract? Well, on the previous slide, I had the rule about subtracting. If you have two things that subtract each other, divide them. So yeah, 100 divided by 4, right? So what's 100 over 4? There you go. So this is log base 5 of 25. Okay, now let's try it in some calculators just to confirm our results. I can't type in log base 5 100, but I can go around it using this rule that we've done last. It's log 100 divided by log 5. And then I'll subtract log 4 divided by log 5. It's 2. Hang on, as I look at these numbers, doesn't that make sense? How many 5's go into 25? 2, right? Because 5 times 5 is 25. Okay, this last one right here, I put down here on purpose, though. Do you see how this has got a little 3 down here and there's a little 5 right here? Those are incompatible with each other. Okay, this is not solvable. Like, not, yeah, I'll just say solvable. So, like, can we still find what its decimal number is? Yeah, sure. You just do log 6 divided by log 3, do log 6 divided by log 5. But you can't actually combine them together as a single logarithm. That's not something you can do. They have to have the same base. Sound good so far? Okay, this change of base rule is actually the first one I showed you. Maybe I should have changed the order around in my notes. But if you ever have like a little base down here that you don't really want to work with, basically take the two logs and divide them by each other. Okay, one thing I have to explain to make sure I'm clear here. It is not valid to just cancel both log signs. Log is not a variable. Log is an operation. So it's not valid for you. Like, let's say I asked you to do 3 plus 2. would it be valid for you to just, halfway through the question say, I just don't want to have a plus sign there. The answer's 32. You laugh at that, right? Because you think that's ridiculous, right? But that's essentially what you do. If you try to erase both of these log signs, that's not how logs work like that. Does that make sense? So it's not a variable to be canceled. Yeah. So let's talk about this one here. How could you type in log base 10 of 10? Well, I mean, your calculator defaults to base 10 anyways, so you could just type in log 10 if you wanted. It's 1. So yesterday I showed you, well, why is it 1? Well, the reason why it's 1 is because there's 1 0 behind it. But another reason why it's 1 is, how many 10s go into the number 10? 1. Duh, right? Does that make sense? But let's say I wanted to write this another way. Let me prove this to you. You could take the log of the big 10 and divide by the log of the little 10. Well, isn't anything divided by itself equal to 1? Yeah. So let's try this one here. To write this one out, it would be the log of the big number, the 3, divide the log of the little number, which would be 2. How many times does a 2 go into a 3?
Like 1 point something.
Yeah, 1 point something. It's not 1.5 because we're not. It's actually has to multiply by itself. So usually these give you completely irrational, like long, never-ending numbers like 1.58. But that's a useful rule, right? Being able to work with a change of base. Again, if you have a TI-84 though, you could go second catalog, find where the logarithms are, if I've shown you this already, and just go log base, and that calculator will actually do it for you.
It's not.
Yeah. So, yay if you have a TI-84. Sorry if you don't. There. How am I doing so far? Does this make sense? Let's try some more examples here. This next one, or actually this is more or less our last one. This is called the power of a log rule. And essentially what happens here is you have an exponent inside a logarithm, and there's an exponent up top. Ooh, I didn't mean to do that. What can happen is you could actually pull that exponent down in front of the logarithm and actually put it down in front. So there's actually no longer an exponent right there, but it's been moved. I might even just show you this one here. Let's do log base 3 of 9. If I write out log base 3 of 9, can 9 be written as like something squared? 3 squared?
Yeah.
So would it be valid for me to write it as log base 3 of 3 squared?
Oh.
Does that make sense how I've taken this 9, turned it into a 3 squared? Well, the way this would work then is that this 2 is allowed to drop down in front of the entire logarithm, which would give you 2 log base 3 of 3. Now I want to ask you a question. How many 3's go into the number 3? 1.
So we're going to do 2 logs.
So it'll be 2 times 1,
So it's 2.
which is 2. Hang on, let's try this another way. How many 3's go into the number 9? 2 of them, right? 3 times 3 is 9. Or, to confirm a third way, log of 9 divide by the log of the little 3 gives you 2. 3 different ways of solving this, all of which tells us the answer is 2. Okay, this one right here, does this one have an exponent?
Oh, but it has a check mark.
Well, sorry, that's not meant to be a check mark. It's meant to be a square root sign.
Okay.
Because this is a good time for review. Do you guys remember what the exponent is on square roots? Good, yes. Yeah, there we go. So it's actually log base 3 of 27 to the 1/2. That's what square roots are. They're 1/2 exponents. Well, now I have an exponent. So according to the rule I'm trying to show you here, you can take that exponent and drop it in front of the whole thing. So now what you have is 1/2 of log base 3, 27. Well, here's my question. How many 3's are there in the 27? 3, right? 3 times 3 is 9, times 3 is 27. So this whole bit right here is the number 3. What is 1/2 of 3? 1.5. Okay, now let's just double check in our calculators. Because for right now, you at least could just type this in a calculator, right? You could go the log of the big number, which is the square root of 27, and then divide by the log of the little 3. Yeah, look, 1.5. That makes sense. Okay, those are the 4 log rules. Here's my conundrum. I think they're very easy for me to show you, and most kids, when I show you the log rules, they go, yeah, no, I followed. My issue is that on the diploma, I don't know how they're going to assess this. There is an outcome that says students have to know the log rules. How they're going to test you on it, though, it can take a lot of different formats. So I'm going to try to do a few more example questions, then I'll show you a couple diploma questions. This is the sort of thing where you really need to put some practice in on this, I think, because you can't just look at it once or twice and say, yeah, no, I got it. It definitely helps to have a little bit of muscle memory built in where you've practiced so that you can kind of recognize the scenarios. So let's try some examples here. Could we simplify this? Now, one thing I want to advise against is the urge to just type it straight into your calculator. It will work. I promise you, that'll work. Here's the thing, though. On the diploma, they like to do things like throwing in the letters A's and B's and C's so that you can't type it into your calculator. Does that make sense? So it's really good just to practice the fundamentals rather than always defaulting to the calculator first. So does anybody see a rule we can use on this? Yeah, the subtraction means dividing. So that means that we have log base 2 of whatever 48 divided by 3 is. It's 48 divided by 3.
16.
Cool. And then we have to ask ourselves a question. How many 2's go into the number 16? 2 times 2 is 4, times 2 is 8, times 2 is 16. So 4. Now that we've kind of done that by hand, using kind of some of our, using our brains first, after that, I don't want to discourage you. Feel free to use your calculator afterwards. But if all you're ever going to do is what I'm going to do right now, I think you're depriving yourself of the skills you're going to need. Because you could type in log 48 divided by log 2, subtract log 3 divided by log 2, and it'll give you the number 4 as well. My fear is that I don't know that you're practicing the rules the way you need to. So, did that make sense though? Let's try another one. Okay, so what sort of rule can I play here? Same one as last time, right?
Just a reminder that English 8A, we're going to be in room 211.
So we need someone to do 18 divided by 3 over 2.
It's not
Let's just make sure that we do that carefully here. I'm going to do 18 divided by bracket 3 over 2. Good, 12. Awesome. Okay. So it means that that's the log of 12. So here's a bit of an issue then. Does 2 go into 12? I mean, 2, can you grab the door button? 2 times 2 is 4, times 2 is 8, times 2 is 16. 12 is kind of halfway in between there. So it's not going to be a 3, it's not going to be a 4, it's going to be a decimal number. So there's 2 main ways you might get asked to answer this. One of them would be to leave your answer like this. Another might be to write it like log 12 divided by log 2. And then the final answer might be to write it as the log of 12 divided by the log of 2 and actually find what the decimal number is, which is 3.58. Any of those are valid. If they ask you for this one right here, I think that's pretty easy to do. But what if they ask you to write it in the form log of A bracket BC, and they make it numeric response? Then you'd have to say your first number is 2, your next number is 1, your next number is 2. Does that make sense?
Yeah.
So don't always just cheat and go right to the decimal number, because I think that, like I said, this is depriving you of the skills you're going to require going forward. That work? Let's try the next one. Okay, so you might be recognizing that, hey, look, there's a subtraction sign again. Awesome, that's great news. But there's actually one more twist on this one. There's a 3 in front. You cannot divide these with a 3 in front. It would be like if I gave you 3x plus 7y. These two things are not the same as each other. Well, not that we can't do anything, but we have to use one of our other rules. You know how you can take an exponent and put it in front? You can take a number in front and put it back up as an exponent is actually allowed. So you could write this as the log base 5 of 40 minus the log base 5 of 2 and make it 2 to the power of 3. See how that works? I've taken this 3 and I pulled it up top as an exponent. We're almost to that point. I want to do one more step if we could first, though. What is 2 to the 3? 8, yeah. So it's the log base 5 of 8. Okay. So now I say now divide. So what is 40 divided by 8? Okay. So now we have the log, still base 5 of 5. And I don't think you need a calculator for that. How many 5s are in the number 5? Ta-da! Okay, let's just confirm. I mean, we can do this the long way as well. Or like I shouldn't say long way, but like using your calculator. Would be the log of 40. Divide by the log of 5. That gets you that first little bit here. Subtract 3, big bracket. Log of 2, close that bracket. Divide by the log of the base of 5, close that bracket. And then one more bracket because I opened like one here and there. But yeah, we got the number 1. That makes sense. I think more than anything else, though, this is one of those things where you can watch and you're going, yeah, I follow. You have to practice, though, okay? It's not one of those things where you can just be like, I've spent 5 minutes on it. Okay, this is a diploma question. Now, this one came off of the -1 exam, so this one might be a little bit more challenging than you're required, but I'm going to make sure that I do a thorough job of showing you how they might phrase the question here. See how they've thrown in X's, Y's, and Z's? By doing that, it makes it a lot more challenging to just use your graphing calculator. And so I don't know whether they'll give you something this complicated on the -2 diploma, but this really tests your knowledge of, well, do you still know how all these rules work? So let's give this one a try as a group here. You see how there's this 2 sitting in front of the log? Well, sorry, what was that? Where's there an equal sign? That makes sense. Cross multiply is where you have an equal sign to cross them across. So, I mean, nice thought, right? But it doesn't fit the scenario. You see how there's this 2 right here, though? There's a rule about that says that you can pull the 2 up as an exponent. So you could say it's log x squared. And yeah, you've noticed the same thing here. See how there's a 3 up top there? That means that you could have log y, but now it's to the power of 3. So that's kind of clever. You can actually do the same thing with this guy right here. Now, this is why I don't think they'd test the -2 kids on it, because this was super sneaky. But you see this middle thing right here? You could write it as 1/2 of log z. See how, like, there is kind of an implied a 1 in front of it there? It's sneaky. Do you guys remember what happens when you pull a 1/2 up as an exponent? It makes it a square root. Square roots are 1/2s.
Wait, what?
Okay, I lost you. Okay, so if you ever have like x to the 1/2, it means it's the square root of x. Remember this rule?
Yeah.
That one for sure you need to know. Okay. Now, what made this one tricky here is that this little piece right here, this log of z over 2, it's really sneaky because you could write it as 1/2 of log z. It's kind of the same concept. There's a number in front. The number in front is 1/2. If you pull that 1/2 up as an exponent, it gives you log of z to the 1/2, which means that you can square root z. And that's why you see how this one, and that one all have z with a square root. That's where it came from. So putting this all together, this is the log of the square root of z. What ends up happening is, see how these 2 are subtracted? Subtract means divide. This one is added, though. Added means multiply. So we need one that has the z one being divided, and we need this one being multiplied.
But does it multiply on top or
It goes on the top, yeah. Because what ends up happening is it's this one added to this one. These are the top of your fraction, and then this one's the bottom. So the answer was A on this one.
I was close.
Okay, if that went a little bit above your head, that's fine. Please don't freak out. I just wanted to show you that as an example of how on the -1 diploma, they were particularly cruel. Here's the reason why I want to show you that. The outcome between -1 and -2 is identical. Okay, now -2 is typically at like a lower difficulty level, but the outcome that I'm supposed to teach you is technically the same. So that's why I want to make sure I'm thorough in trying to show you some of the challenging examples. Because if I made this question be 2 log 4 minus 1/2 of log 7 plus 3 log 2, you just type that in your calculator. Does that make sense? So they're going to challenge you by throwing in x's and z's and y's to see whether you really understand how these rules work. Do I have one more still? Okay. Here's one that I believe came off of a -2 diploma, however. This is one where a student was asked to do some work, and I think I've talked with you about this before. They asked you to find a mistake. Yeah. So this is the sort of question where, although I will ask you to do some written work once in a while, the diploma won't. This is how they mitigate that. They're gonna ask you to find mistakes, right? So we need to look through their work and say, okay, well, where'd you screw up? So let's do it one at a time. Here, this guy right here looks like it's turned into this thing below it. Let's walk through, see if they did it right. It looks like they took the 2 and they brought it up top.
So they did it wrong.
Well, what happens with your exponents? What happens when you have x to the 4 times by 2? It times this together to give an 8. So that one was done right. Take a 3, bring it up, times it by a 2. That's a 6. Oh, that's good. Take a 4, bring it up, times it by a 3. That's a 12. So your mistake was not in step 2. They didn't script in step 2. Then on the next step here, what they did is they took the 8 and the 6 and they subtracted. Well, subtract means divide. So see how the 8 and the 6 have been divided?
But the x12 has to be on top.
Yeah, but see how the x to the 12 is the plus? That actually should have been sitting up top here. So that was a mistake. So the answer to this question, by the way, was B. But I'd like to keep going, though, because I believe this one said the student's first recorded error. They might put more than one mistake in there just to see whether you picked the wrong one. Because I think there's another mistake, actually. Well, okay, so then what you do in this case here, that's a good question. You'd assume that the next step is correct and then go from that step to the next one and see whether that is right. So how do I phrase this? Assume that now step 3 is actually correct. Did they do step 3 to step 4 correct? And I would say yeah. Because look, see how what they did here? They took the 6 and the 12 and they put them together to get an 18. If step 3 was right, step 3 to step 4 would have been correct. The problem is step 2 to step 3 was actually wrong. One more step here. 8 and 18 is not 10 though. Because the 10 is on the bottom. Does that make sense? The bigger number is on the bottom of the fraction. So this should have been written as log base A of 1 over x to the 10. So they actually made a second mistake going from step 4 to step 5. That makes sense? Okay, that was a -2 level question, just so you guys are aware. So they might not actually be able to test that you can use the log rules, but I feel pretty comfortable in guessing that this is one of the ways they'll mitigate it. They'll show you someone's work. Do any of you guys have the assignment number 9 nearby?
Yes, right here.
Can you guys find the assignment number 9? I'm going to show you one of the questions off of it that I give as a practice one. It's number 8. So granted, that's a little ways off. We're going to talk about how to solve number 8 a little bit more in detail tomorrow, but this has kind of got the same sort of concept. This used to be an old written response question that they took off of diplomas from years and years ago when they actually did written stuff, where the question was essentially, here's student A and here's student B, and they both did some work. And here I'm going to tell you they both messed up, actually. I'm going to tell you that this kid messed up and this kid messed up, and I'm going to ask you to find the mistakes. I saw a question a few diplomas ago, though, where they showed you 2 students' work, and the question was, like, which of the following statements is correct? Student A got it right, student B got it wrong. Student B got it right, student A got it wrong. They both got it right, or they both got it wrong. And those are the 4 answers. Does that make sense? So, like, A is you're right, you're wrong. B is you're right, you're wrong. C is you're both right, and D is you're both wrong. And the question was, look over their work and tell me which one of these things is true. And so, although this isn't quite the same thing, it's a similar concept where the question is, look at the 2 lines of work and tell me, are they doing it properly? We can talk about student B's work tomorrow, but let's talk about student A's work right now. Look, here they did 3 to the x plus 2 equals 6 to the x. And they tried to turn 6 to the x into 3 to the 2x. Why is that wrong? Yeah, 3 to the 2 is actually 9, not 6. Does 6 have groupings of 3 in it?
Yeah.
Well, okay, you gotta change your brain though. Like, it's not 3 times 2. It needs to be like 3 times 3 times 3 times 3, right? And so 6 is not a grouping of just pure 3s, right? 3, 9, 27, those are the ones that work. So this is actually where their mistake was. Trying to turn a 6 into a 3 squared is where they went wrong here. Does that make sense? Student B, we're going to talk about solving tomorrow, because that's tomorrow's topic. Using some of these log rules to solve something. So they did make a mistake, but I'll point their mistake out tomorrow. So, that was in my notes, right?
Yeah.
Okay, so let me just do a quick summary, then we'll take a break. I hate to tell you this, but you're probably not going to like this section. Okay? Dash 1 kids don't overly like it. Dash 2 kids probably won't like it. Okay? It's probably one of the harder things we do. There are 4 rules you need to know. Okay? Basically, multiply means add, divide means subtract. If you have a little exponent up top here, or a coefficient in front, you can move them back and forth. And then if you ever have a base that you don't like, you can just divide them. You have to put a log on both of them to divide. Okay? The question is, though, can you use these rules to help kind of solve the question? Chances are it's going to be like a numeric response kind of question, or they're going to ask you to look at someone's work and find the mistake, or they're going to put in X's and Y's and Z's or A's and B's and C's just to make it challenging. So I will do my best to try to find you as many examples as I can at dash 1 and dash 2 levels so that you're prepared. But you got to practice this stuff. So, sound good? Okay. Take a 5-minute break. When you come back, find something to practice, I guess. I asked you to do 5 of these in your journal. I don't think 5 is all that many, though. So you may want to try a few more than that. 6. Okay. Take a 5-minute break or something.